So now that we're familiar with graphing points, let's start looking at doing some more graphing. So in the last lesson, we talked about how we can convert patterns into equations. Okay? So here we have an example where we've got the figure number, which is made up of little squares, and we are finding the relationship between the figure number and the perimeter of the shape. Okay? So let's go just like we did the table before. So we'll have rectangle number, which we're going to call little n. And we see we have 4 of them here. And we want to find their perimeter of each one. Which we'll call capital P. Remember what perimeter means. It's the distance around an object. So what's the perimeter if each of these is 1? What's the perimeter of figure 1? 6, right? 1, 2, 3, 4, 5, 6. We don't count the one inside because that's not, remember, perimeter is distance on the outside. So it's 6. How about the next one? 8. You guys can probably see the pattern already starting to develop. What would be the next one? And then? Right. So this is what we did in 7.1. And then what we did is we made an equation out of it. And then we answered some questions. Now what we're going to do is we're going to see what it looks like visually. So what we did actually when we plotted the rectangle, when we made the rectangle number and the perimeter, we made a coordinate. So I'm going to turn this into the coordinate 1, 6. I'm going to turn this into the coordinate 2, 8. This is going to become 3, 10. And this is going to become 4, 12. Well, I can plot these points. Okay. And we're going to use the grid below to plot. Now remember, when we first did the graphing, we did the 4 quadrants, right? And because sometimes we got negative numbers, but none of these are negative, are they? So what we're going to do is we're not going to do all 4 quadrants. We're going to graph the first quadrant. Because in the first quadrant, everything's positive. Now, normally, we call the horizontal axis what letter? X, right? But what is it called in this problem? It's the first column. What's it called? So it's called N in this one. But we treat it like X. This is normally called Y, but here it's called capital P. So what we have to do is we have to label each axis. So this is the figure number. And this is the perimeter. Now, normally, every grid line we go up by 1, right? But we don't have to. We can go up by 2s if we want. We can go up by 4s. We can go up by 1,000s. It doesn't matter. Okay? How do we know how much to go up by? Let's look at the numbers. Pretty simple numbers, right? Like I just have to make sure that I can do 1, 2, 3, 4 here. Don't write this down. But if I did this, if I said every one and I did 1, 2, 3, 4, 5, 6, don't copy this down yet. What's wrong with that?
When you thought it might just stay in the environment.
Sorry?
When you thought that it'll be kind of squished.
Yes, exactly. Right? So that's not a great, what we call scale. Maybe what we should do instead is every 2 we'll call 1. So we'll go up by 1/2. No, they can be different. Good question. So let's do this instead, because that way it'll be more spread out and it'll be easier to sort of see. So yes, just like Finley asked, we're going up by 1/2 every time here. We don't have to do that with the perimeter. We can go up by whatever we want. It doesn't have to be the same for both of these. Well, what numbers have I got for perimeter? 6, 8, 10, 12. Remember, we have to start at 0. I have to make sure 6, 8, 10, 12 are on my grid. If I go up like 2s, that's not, like if I went 2, 4, 6, 8, 10, 12, pretty close. But that's, I'm almost going off the graph, aren't I? Okay. So maybe what we do, let's say every grid line is 2. So 2, 4, 6, 8, 10, 12, okay? Notice you don't have to write every single one. You don't have to write 2 here. You don't have to write 6 here. Oh, wait a minute. I made a mistake. 2, 4, 6. Oh my God, I made a big mistake. 2, 4, 6, 8, 10, 12. Yeah, sorry. So 2, 4, 6, 8, 10, 12, 14. I don't have to go any higher. So notice on this scale, I went up by 2s. What's wrong? Okay, don't erase this. But what if I did this? Because this is a common mistake students will make. You don't have to copy this down. What's wrong with that? Sienna? Right. Notice from here to here, I go up by 6, and then I go up by 2s. You can't do that. You have to go up the same amount every time. So yes, this would have, to get to 6, you'd have to go 2, 4, 6, 8, 10. Good question, or good job. Yeah, Sadie.
Why didn't go over 12 and over 4?
Over 12 and over 4?
In the pattern, it only goes to 4.
Oh, you don't have to. I always just do a little bit extra, that's all. Okay? Because the pattern could continue, right? Okay, so let's plot our points. So what are the points we have? 1, 6. So according to our graph, 1, 6 would be here. 2, 8, 3, 10, 4, 12. And I suppose we could keep going forever. Now, here's an interesting question. Should I draw a line through the points? Like a lot of times we don't just see points, we see lines. So don't copy this down. But like, would you say that's acceptable or unacceptable? Why? Yeah, like, does this go into the negatives? You can't have a negative figure number. You can't have a negative perimeter. So you're right, it has to start here. Okay? So that's one thing. We can't draw just a line through it. Okay, what if I did, let's say, well, let's say it starts here. Is that acceptable or unacceptable? Yeah, that doesn't really make sense, right? Like a figure number 0 has a perimeter of 4. That seems a little silly. Okay, all right. Would that be acceptable or unacceptable? It makes more sense, absolutely. We definitely shouldn't have Bodhi here, and we definitely shouldn't have an arrow going that way. But think about what these represent. The figure number. Yep.
We did it where we did it like kind of in the middle between both of them, like not on the exact page. It was like trying to,
Like a dash line?
no, you don't have to be touching. Yeah, like it's just like the general, like,
Not quite sure what you mean.
she tried to, like, when we did basketball, you were told that the line that you draw between the dots doesn't have to connect to the dot, but it has to be in the near area.
So, okay.
Like, you know,
Well, hang on, let me see if I got this right. So like that? Right? Not like that.
I was trying to show.
Sure. Oh.
Yeah.
Uh-oh. Do you have a problem with that, Santa? You sure? All right. I have actually never seen that before. So think about it this way. Figure number 1 is 6, right? If you had a line here, you're telling me that figure number 1.5 is going to be 7. Does that make sense? Can you have a figure 1.5? No, it's either figure 1 and 2 and 3 and 4 and 5, nothing in between, right? So if it's nothing in between, we do not connect the points. However, we need to show that it goes forever, like it keeps going. So what do? I draw just a little arrow on the end like that. That just means it's a series of points that keeps going, but I don't connect points because you can't have a fraction of a figure number. You can't have a fraction or part of a figure number. There is no such thing as figure 1.5 or figure 2.76. It's 1, then 2, then 3, then 4. So one thing you got to be aware of when you do these kind of questions is whether you connect or not. Let me show you an example. I know I'm jumping around a little bit here, but let me show you an example of where we would connect. Let's say we had another one. And let's say somebody was driving or somebody was walking or running or whatever. Okay. So at 0 hours, well, they haven't gone anywhere. After 2 hours, looks like they've gone 40 kilometers. So I would suggest maybe they're biking. If they're driving very slowly. If 4 hours, 80 kilometers. Notice the points are connected here. Why do you think these should be connected, but the other graph shouldn't be? What's that? Well, the other one kind of points at 0 too. Well, no, not really, but not quite. Finley?
When you're talking like 1.5 hours, then you'd be at like
Yeah.
1.5 for like 30 kilometers.
Can you have a fraction of time? Yes. Right? I mean, like, time doesn't go by like 1 minute, then 2 minutes. I mean, we count seconds, right? And there's time in between seconds. So time is what we call continuous. You can have fractions. You can also have fractions of distance, can't you? Like it's possible to cycle 20.83 kilometers, right? So that's why this one is connected and the previous one was not, okay? Like if I don't know, somebody's running in the roof or something. What if I said this one? Sure. And then the cost, depending on how many shirts. Would you connect that one? You could, right, you can't have fractions of shirts, which means if one of them you can't have fractions of, you can't draw a line through it. Okay? So in this one, you'd have to put just the dots. You could not draw a line through them. So you got to think, some things are continuous, you can have fractions of. Other things are not. So yes, like time, distance, weight, money, you can have fractions of money. Okay. All right. So now that we got that cleared up. Remember in the previous exercise, we talked about how to write an equation. What's the equation of this? How do I calculate the perimeter? What's the equation? Remember how to find the equation? How much are we going up by? The perimeter goes up by 2s. Doesn't that imply times 2?
Yeah.
So 1 times 2 is what? How many short am I? 4. 2 times 2 is 4. I'm 4 short. 2n plus 4. Because we're always calculating the second variable. So p equals 2n plus 4. Okay. But you see what a complete graph looks like. Don't forget your Vegas. Okay. So some math words. You don't have to memorize definitions or anything like that, but you do have to identify. And I don't know, you may have taken this in science. So the perimeter depends on what figure number we're talking about. So therefore, we call the perimeter, or the y value, the second one, the dependent variable. And if p is the dependent variable, n will be the independent variable.
I think variable always by.
Yes. But sometimes we may have different names for them, right? Like in our problem, this was called little n, and this was called capital P. Remember, the horizontal one is always the independent. The vertical one is always the dependent. If you're given a table, the first one is always the independent. The second one is always the dependent. Okay. So this is a huge part of math. I'm sorry, guys. Am I interrupting you? I'm so sorry. Was I bothering you? I'm terribly sorry. Do you need some help? You okay? You understand?
Yeah.
No, I know. I'm just joking. Because I'm a funny guy. Okay. All right. So what we're talking about here is a relationship between two variables. That's a big part of math. Okay. Much of what we do is we talk about a relationship or a relation between one variable and another. And we can always graph these relations, show a visual picture of them. Sometimes, or many times, the graph looks like a line. Other times, which you guys will see starting in grade 11, they look like curves. Okay? We're only going to focus on the ones that look like lines. So when the graph of any relation is a straight line, or you can draw a line through it, we call it a linear relation. Okay? In a linear relation, a constant change in one variable, usually the independent, but that independent, produces a constant change in the other. Which would be the dependent. So if you look at this problem that we've been working on, every time the figure number increases by 1, the perimeter increases by 2. So there's a constant change in the first variable, and that produces a constant change in the second. And they don't have to go up by the same amounts in each column. So in that example that we did, every time the figure number went up by 1, the perimeter went up by 2. Okay? That's the very definition of a linear relation. Okay? So the one we did, even though it was just a series of points, we could still draw a line through them, so it's a linear relation. This is a linear relation because it forms a line. If I did something that had a curve in it, it's not a linear relation. Okay? All right, so let's look at some examples now that we kind of did that. So we're going to practice some graphing. Oh, I got to change this example. DVDs. Anybody actually watch DVDs anymore? No way. Sometime?
Yeah.
Okay, all right. Yeah. Maybe you even rent them anymore? You can buy them, but I don't think you can rent them anymore. Oh. I never thought of that idea. Okay. So we want to graph this data. Remember, everything's positive, so we don't have to draw 4 quadrants. We're going to draw this. And the first column is always independent. Second column is always dependent. Which means on the graph, the horizontal will be the independent, the vertical will be the dependent. Okay? So yes, I'm going to put that. Independent, dependent. Always. And so remember, instead of Y, we call this capital C. And instead of X, we called it little d. How much do you want to go up by in the DVDs? 2 would be 1?
Yeah.
So 1, yeah, I think that's good. Because then they're pretty spread out. If we just did 1 to 5, it would be very squished. Remember, we have to start at 0 for both of them. What should we go up by for the cost? Remember, you can go up by anything you want, as long as it's the same amount every time. You don't have to go up by $1. You don't have to go up by $2. You don't have to go up by $5. You can go up by $2.50 if you want to. It's up to you. So what do you think you did?
I think you go by 4, like 4, 8, 12.
Okay,
Backward.
like, but, so this would be 4, 8, 12?
Oh, no, by 2. So like,
So 4, 8, 12, 16, 8, yeah, that's pretty good. Okay, that would work.
all of them go like 3 bits every time. So then you just do like 2 and then 350. But then second,
Yeah, we could do that. You could go up by 350 every time, because that's what it's doing in the table. But it's not the only answer. Like Zara, what you said is just as correct. Okay? So yeah, we could go up like that, because every 2 grid lines, we're going up by 350. That's fine. We could have done every 2 grid lines, we're going up by 4. We would have had to do some estimating, but that's fine. It still works. Okay, what are my points? Well, if I sell 1, what's the cost? So wouldn't that first one be there? 1, 350. Then 2, $7. 3, 10.50. 4, $14. 5, $17.50. Okay? We assume that we could keep going forever if we wanted to. So we're going to have to put an arrow on the end. The question is, do I connect? Why?
Because remember, it's the same as number of bigger numbers, you can't.
You can't have a fraction of a DVD. You can't rent 3/4 of a DVD. You can either rent 1 or 2 or 3, nothing in between. So do not connect. But to show that we can keep going, put that little arrow on the end. Yeah, we still got one more question in this. Is this linear? Could you draw a line through all the points, or would it be a curve? Like if you were to draw a line through the points, would it be a line or would it be a curve? It'd be a line. That means it's linear. So we would say it is linear because the points form a line. I don't know why this rectangle keeps following. Weird. If the points didn't form a line, then we couldn't say that it's linear. Okay. All right. Next one. Well, this time we're not really. Sorry about that. Oh boy. Is there a lockdown? Oh, yeah, because there's nothing came up on my computer. Okay. All right. This one, it's not a word problem, which means we could have negative numbers. Okay. So, first thing we have to do is create it. X is the independent, Y is the dependent. And it's telling you to choose the X values 0, 1, and 2. It's telling you to choose those ones. If X is 0, Y is going to be 4 minus 3 times 0. Let's here. 4, positive 4. 4 minus 0 is 4. So therefore, that's the point 0, 4. What about if x is 1? Well, this time it would be 4 minus 3 times 1.
So it's one.
So it's 1. That's the point 1 comma 1. I know what the
Wait, I don't,
yeah.
I don't see how you apply the rule. So,
We need a apply the rule.
well, can you just explain how you got the y equals?
Well, this is the equation, right? Up here. So I decided to choose 0, 1, and 2 for x. So if I plug 0 in here and calculate this side, y works out to 4. Right? If I plug 1 in here, y works out to 1. If I plug 2 in here, what would y work out to? -2. Yeah.
So did you just basically make your own?
Well, yeah. Exactly. You're allowed to do that. So let's graph these points. 0, 4, 1, 1, 2, -2.
Where you go, it's my first.
Which way? Yeah.
Why is it going up and 0?
Well, 0, 4.
Oh,
Do I draw a line through them? You sure? Can you have fractions? Is it a word problem? No. So you could have fractions. Can you have negatives? You bet. Whenever the variables are x and y, always draw a line through them. Always. Because it's not a word problem, which means we can choose anything we want for x and y. Fractions, negatives, whatever. So connect. And then finally, is it, so this is A, this is B. So therefore C, is it linear? Don't overthink this. Is it linear?
Yes.
Absolutely, because it's a line. What word is in linear? Line. Yes. Clearly it forms a line. Okay. We're back to a word problem. Student Council is planning to hold a dance. The profit in dollars is 4 times the number of students who attend, minus $200 for the cost of the music. Okay? How do I convert that to an equation?
Could you do 4 times this 4s minus 200?
Yes, equals,
Cost, C.
well, in this case, it would be profit.
Oh,
So we could call it P. So yes, capital P for profit is going to be 4 times the number of students minus 200. That's exactly right. So we call the profit P. We call the number of students N. So that's how we got our equation. Now we're going to graph this equation. So we're not going to use X and Y. We're going to use P and N. N goes first. In an equation, the variable by itself is always the dependent variable. So we need to make up some numbers. Would it make sense to calculate one student? Not really, because you got to think there's going to be quite a few students attending. 20, 40, and 60, sure. You could do 50, 100, 150. Okay, but sure, let's do 20, 40, and 60. So 20 students attend. The profit is going to be $4 for each of those 20 students, but we got to subtract 200 away. What do we get? Ooh. Yeah, so that's negative 120. That means that the student council loses money. It is possible to lose money. It is possible to have negatives. So this point is 20 negative 120. 4 times 40 minus 200. Still in the negative, still not making some money. What about if 60 students come? So finally, we're making some money. Finally, with 60 students. So obviously, we want more than 60 students in order to make more money for the student council. So now we got to graph this. Notice I have negatives for the second column. So I am going to have to do this. Because we have to make room for the negative y values. We can't just go here, here. So our zeros are going to be here. This is the number of students. Which we have called in. I'm just putting it down here to keep it out of the way of the graph. And this would be the profit, which we have called capital P. Or actually, what do you want to go up by on the horizontal? Notice we got 20, 40, and 60. Okay, every one or every second one? Yeah, I would say every second one. Okay, so we'll go 20, 40, 60. So really, we're going up by tenths. What would you want to go up by vertically? Up and down. I've got to get down to 120. So how much should I go down by? 40s. So this would be, we could go negative 40, negative 80, negative 120, that would work. Yeah, if we did negative 12, we don't have enough space. Now, because we went down by 40s here, that means we got to go up by 40s here. Okay, you can't change the scale. If you're going down by a certain amount, you gotta go up by the same amount from 0. So let's plot our points. 20, negative 120. 40, negative 40. And 60, 40. And of course, the next question, do we connect? No. Can't have a fraction of a student. Do not connect. But we assume we can keep going up, so we'll do those. Whoops, that's not really in line. Do it more in line. Okay. Now, the last question. How many students have to attend to make a profit? 60? Well, 60 will give you a profit, right? Could fewer attend and still make a profit?
No.
Really? Yeah. What if 50 attended? What would be the profit if 50 attended? Look at your equation. If 50 of these attended, what would be your profit? What's 4 times 50? 4 times 50. 200 minus 200? 0. So if 50 students attend, you make no money, but you don't lose any money. So how many would have to attend? At least 51 before you start making money. So here's how we could answer. We could do this. Remember, P is equal to, what was it again? 4n minus 2. And we want to find what's n when there's no profit. So we have to solve this equation. So we add 200 to both sides, add 200, and we get 200 equals 4n. Divide both sides by 4, and we get n equals 50, right? So that means no profit, which means 51 must attend. As soon as that 51st steps in, you start making money. And every other person after that, you're making more money. So if you're planning out this dance, if you guys are in the student council 3 years from now and you want to actually host a dance, something that hasn't been done here in I don't know how many years, probably be helpful to know what your profit is. Okay.